This survey provides a comprehensive overview of panoramic vision, bridging the gap from perspective to 360-degree understanding. First, what's panoramic vision? Here is an example of what panoramic vision is. Different from perspective images, panoramic vision captures the whole 360-degree spherical world. With proper hardware, we can immerse ourselves in the full environment, as if we were standing right inside the scene and freely looking around in any direction. Panoramic vision is widely used in real-world scenarios, and using panoramic data requires projecting the spherical world onto 2D faces. So it is important to understand these projection patterns. This figure illustrates several common panorama projections. Equirectangular projection, also known as ERP, is simple but distorted. Cubemap reduces distortion with 6 faces. Icosahedron gives uniform sampling, tangent works like perspective patches, and Panini preserves vertical lines. ERP is the mostly used representation, and its geometric properties introduce critical gaps between perspective and panoramic vision. So what are the gaps that we want to bridge? From our summary, there are basically 3 gaps. First, the geometric distortion near the poles. Second, the non-uniform sampling. Finally, the boundary continuity in ERP. These gaps explain why perspective methods cannot be directly applied to panoramas. To address these gaps, we make a cross-method analysis. This chart systematically summarizes how different methods are applied across panoramic tasks. Among all the approaches, we highlight the 2 common strategies: distortion-aware methods and projection-driven methods. Distortion-aware methods adapt the network directly to ERP distortions through feature design or loss weighting. Projection-driven methods reproject panoramas into alternative views like cubemaps and then fuse the results at different stages of the network. Next, we also did a cross-task analysis. We further dive into the 20 individual tasks based on more than 300 research papers. This horizontal comparison reveals task-specific challenges and shared insights across the field. As shown in the table, the tasks range from image enhancement to understanding, and finally to multimodal and generation tasks. Finally, we summarize the promising future works. We categorize this part from 3 aspects. First, the data bottlenecks. Current datasets lack scale, diversity, quality, and multimodal coverage. Second, model paradigms. We need both foundation models and expert models, along with advances in multimodal alignment and panoramic generation. Third, applications. Panoramic vision has great potential in autonomous systems, immersive XR, digital twins, and broader societal areas. The last word: this work would be impossible without the support of our colleagues. And let's shape the future of panoramic vision together.